So, excuse me. Okay, this is where we stopped last class. So remember, here in this section of the class, of the text, we are looking at what happens when you have a p-n junction with a constant voltage applied. So it's off equilibrium, but under steady state. Okay, so you have fixed voltage, and all the transients have relaxed. So you have a fixed current flowing. Because we are trying to understand the physics of how the current, where the current comes from, and how to quantify it. Okay, that's what we did. And just to recap, the picture is as following. Okay, when you apply voltage, you get a carrier injection, right? So let's look at the p-type for a second. So you get electrons that get injected from the n-type across to the p-type. And the basic assumption for the ideal diode approximation is that there is no recombination in the depletion region. So any electron that gets injected from the n side will cross to the p side, which essentially means that it gets swept across by the field, right? Because there are very few carriers. They don't see any other holes. So the electrons coming from here to here, they get injected. And it's a constant injection such that this sort of carrier profile is maintained. Or, right here is what's important, because the concentration here is maintained at some number, Np plus delta Np. Np is the base concentration without the injection. That's the concentration of holes in the, electrons in the p-type material. Then you have the extra injection, which comes from delta Np. Now, because of the extra injection, of course, you get a concentration gradient, so it will diffuse. So you get a diffusion, you solve the diffusion equation, which gives you this kind of a profile based on the diffusion length, which is just shown here. Okay, so the electrons in this case diffuse from right to left, so the current is from left to right. So that's the electron diffusion current, right? Same thing happens on this side for the holes. You have a hole diffusion current which goes from left to right as well. And you have to add them up to get the total current. Okay, that's the concept. So make sure you're fairly clear on that end. Okay, so the few things you will recall is when you add up the currents, you get a very simple diode equation. So like I said, if there is no recombination in the depletion region, then the total current in the material is the current, the electron current at this point plus the whole current at this point. Okay, and the argument there is that there is no recombination in between. So if you calculate them independently, add them up, you get the total current at any point along the bar. Again, remember the assumption is that the current is constant throughout the bar. There is no potential drop across the bar. I mean through the neutral regions of the bar. Okay, that should be pretty obvious, right? So again, that's an important assumption, so keep that in mind. P-type and type, you have the depletion region. The entire assumption is that the current at any point here, any of these points should be exactly the same. And the reason that is because we are assuming there is no potential drop in these neutral regions. All the potential drop happens here. Okay. This comes from Ohm's law, right? Okay, so the diode equation is pretty straightforward. You add them up, you get an expression such as this. You have some constant current in the front multiplied by an exponential relationship to the voltage. Okay, that's the standard diode equation you've seen before. And it basically tells us when you apply voltage, what is the current. For forward bias, it's pretty straightforward. This is exponentially increasing, so you get lots and lots of current. In the reverse bias, you get a negative value here. And if the reverse bias voltage is a few millivolts, okay, this term here basically goes to 0, right? So e raised to minus kT over Q is about 26 millivolts. So if you're a bit more than that, basically this term disappears. So you essentially end up with a voltage-independent current, which is so-called reverse saturation current. Okay, this is the off current, right? Okay, so those are the basic ideas, and this is sort of where we stopped. So the current characteristics are shown here. So that's the current, that's the voltage. You have a very characteristic curve. The key points again to remember is that this constant term in the front is also called a generation current because it comes from the electron and hole injection. So it's a minority carrier. So it's the majority carrier injection from the majority carrier side to the minority carrier side, and then recombination. So the source is actually thermal generation. Okay? In other words, you have to generate electron-hole pairs here for this electron to come across, essentially. Okay? Or another way to think about it is that once the electron comes here, it's diffusing, right? And recombining at the same time. Now, for it to recombine, it needs extra holes. Okay? And those holes recombine with these electrons, so forming a bond. Those holes can also come from the thermal generation, electron hole pair generation. Okay, those are the excess holes. So it's also called a thermal generation current, as shown here. But in any case, you can just calculate it based on the diffusion equation, as shown here. And you can see the important points are shown here. The minority carrier concentrations are the important part because, again, it's the concentration gradient of the minority carriers, right? So, for instance, it is the electrons in the p-type and the holes in the n-type that give rise to this diffusion current. Okay. So the few practical issues which are important here. If one side is heavily doped compared to the other, then the carrier injection from the heavily doped region to the lightly doped region will dominate. What does that mean? That means you have two terms here. If Pn, let's say, is far smaller than Np, which Pn far smaller than Np means the n-type material, which is the holes, is very heavily doped. Okay, that means there are few holes. Then this term can be cancelled. Then it's only that term that matters, essentially. Okay, so you see the correlation. And this is practically important because most devices that are actually made, one side is very heavily doped, which has some, and the reasons for this you will understand later in the class. But it's very common that you have a P plus N junction or an N plus P junction, and so on. Okay. So if P is much more doped than the N side, then Pn is much smaller than Np, then the current is dominated with the holes injected from the P side to the N side. And this is called the P plus N junction. Of course, when you have a highly doped P side, the depletion region on that side is very small too, right? And that turns out to be a key reason why that needs to be heavily doped. Remember, the extent of the depletion region depends on how heavily doped these are, right? If it's very heavily doped, this region goes smaller. Right, because there are few charges needed, few depth needed, because the concentration of charges is so high. So this is an interesting question I want you to think about. So in this situation, let's look at that. How should the doping be changed to double the current? Okay, so if you let's say we have this some equation like this, and let's say we can control the doping in order to increase the current by 2 times. So the idea here is that if it is a heavily doped junction, so P plus N junction, let's say, so Pn is much smaller than Np, so this term goes away. It's only that term, which means it is the doping on the lightly doped side that's important. Okay, does that make sense? Okay, so you have an I now. That is essentially proportional to some term times Np plus some term times Pn. Times all the exponentials. Let's ignore that for the time being, right? If Np is far smaller than Pn, that means p-type is very heavily doped, right? There are very few electrons. Okay? That means this term cancels out, basically. This is too small. So the only control you have in terms of doping is now on the lightly doped side, which is a little bit counterintuitive. In other words, if in a heavily doped, so you have one side heavily doped, another side lightly doped, and you can control doping in order to increase current. The only control really that you have is the lightly doped side. So in order to say double the current, you would decrease the doping here by a factor of 2. Okay, so it's a little bit counterintuitive. So think about this. Of course, Pn is the holes in the electron n-type material, right? And I need to double that basically, right? You see, proportional to that, because that term's gone away. So if I have to double that, what do? I dope that less, the n-type. I need more holes. Okay? It's a little bit counterintuitive, so that's why it's pointed out. So you should think about this a little bit. Of course, how does the depletion region look like? You're very familiar with this now. So the heavily doped region will have a shorter depletion region. So that's pretty straightforward. This is technologically important as many real devices are made in this fashion. And the reason for this, and we skipped that portion of the chapter in the interest of time, but it has to do with the fact that you start off with the silicon wafer. Remember, it's a silicon wafer which gets processed to make the transistors, diodes, whatever. The starting silicon wafer tends to be some lightly doped material, like N-type. It can be P-type, let's say N-type, okay? Then you make your diodes and so on, which means that you introduce a P-type doping into an N-type substrate. So you start with a silicon that's N-type, and you dope it enough with P-type donors, and you make it P-type. Okay? So you end up with a P plus N junction. Remember, we did an example of this. We took an N-type material, put lots of acceptor atoms in it, and made it P-type. Remember, we talked about changing the doping concentration and so on a couple of weeks ago. So that's why it's important. Practically, many devices tend to be this way. Okay, so the next part of this is to understand how do the Fermi levels vary across the junction when a voltage is applied. Now, the first concept, of course, is that at equilibrium, the Fermi levels don't change. They have to be fixed across the device. There should be no variation. But when we have a voltage and when you have current flowing, it's no longer equilibrium. Okay, so you would expect that the Fermi levels have to change. Now, the intuition that, before we look at the math, is essentially that recall that the Fermi level relate to the valence or conduction bands gives you an estimate of how many majority carriers are there, right? Or minority carriers, they're both related, right? So if you have a spatial variation of carrier concentrations, one would expect a spatial variation in the Fermi level, okay? But now this Fermi level is under non-equilibrium conditions, and it is referred to as a quasi-Fermi level. Okay? And you will see more about this actually next week on Thursday's lecture on optical excitation. Then it'll become a little more clearer. But the intuitive idea is that the Fermi level follows the carrier concentration. And the fact that the Fermi level is constant under equilibrium is the fact that in the neutral regions, the carrier concentrations are basically constant, right? There's no spatial variation. The only spatial variation happens here, but still the Fermi level at equilibrium is constant across because the bands will bend to compensate for it. Okay? So the carrier concentrations under equilibrium conditions are constant. The only change happens in the depletion region. And the bands bend for that. Okay? When you apply a voltage, something different happens. Right? When you apply a voltage, you end up with a carrier concentration, minority type, but the same thing happens to the majority as well, right? The minority type, which changes with space, right? Now recall that if I were to plot the band diagram here, okay, here there are many more holes. So okay, let's try to do this. It's intuitive. Let's start at this point, okay? This point, there are many more holes. And remember, this is the p-type. Sorry, many more electrons. This is the electron curve. Minority carrier concentration exponentially decreases in the p-type material. Of course, let's start with far away. Far away, the electron concentration is the same as under equilibrium, right? Because it has all the extra electrons are diffused and recombined away. So far from the junction, you would expect the Fermi level to be the same as before. P-type, so it will be close to the conduction band, right? That's obvious. As far away, the excess electrons have disappeared. As you get closer to the junction, there are more electrons than the equilibrium situation. Okay? When there are more electrons, what happens is that the Fermi level, under non-equilibrium conditions, the Fermi level splits. In other words, you have one Fermi level for electrons, another Fermi level for holes. And those are called the quasi-Fermi levels. Okay, this is the non-equilibrium condition. So this Fermi level is for both electrons and holes, because it's far away. As you get closer to the junction, they start splitting. Okay? So you get a Fermi level for holes, which is about the same as the original Fermi level because the majority carrier concentration dominates and the concentration of holes really doesn't change very much. You get a few extra holes because you get a few fewer holes because of the recombination. That's a very small number compared to the excess doping that's already there. Okay, so the Fermi level for holes basically remains the same as before. But for electrons, because you have more electrons, the Fermi level gets closer to the conduction band. Remember the concentration of electrons is determined by the difference in the Fermi level and the conduction band, right? Same definition for the quasi-Fermi levels as well. We will introduce this mathematically next Thursday, but I want you to understand this conceptually. So one would expect Fermi level for electrons to go up. Okay. Okay. And on the other side, the opposite happens. Okay. So you see, far away, you have a Fermi level which is close to the conduction band because of N-type. Okay. That is the same as equilibrium. But as you get closer to the junction, there are more holes here because of the carrier injection. So the quasi-Fermi level for holes start going down. Right? There are more holes. It gets closer to the valence band. Okay? And then the quasi-Fermi levels meet, actually. And these quasi-Fermi levels. And this difference between the quasi-Fermi levels is the applied voltage. Okay? Which intuitively should make sense to you because the applied voltage, remember, controls the injection of the carriers, right? And this difference when they split has to do with the excess carriers, excess minority carriers, right? You see that, right? So for instance, in the p-type, the original Fermi level starts going up because there are excess electrons here, right? And the maximum deviation happens right at the junction where you have the biggest voltage difference. You have the biggest injection of electrons. Okay. Now, which is basically what's here. So you have the carrier injection. So you have electrons going from here to here. You have a diffusion which happens. Holes going from here to here. You get a diffusion happens. If you look at the Fermi levels, it's what I drew. Far away from the junction on the p side, you have a Fermi level which looks like equilibrium. As you get closer to the conduction, closer to the junction, they split into two Fermi levels. You get a whole Fermi level which remains about the same as equilibrium because it's a majority carrier. It doesn't really change much. The electron Fermi level actually starts going up because there are more electrons there. I exaggerated this obviously, right? You can see. Then on the other side, the opposite happens and the two Fermi levels do meet. Okay? And the difference between them is the applied voltage. This is forward bias. And of course, reverse bias, the opposite thing happens. Okay. This is a little bit of a complicated concept, this idea of quasi-Fermi levels. So before we think about this mathematically, I want you to kind of picture this, of what might be happening. Okay? I'm going to look at this mathematically next week. Yeah. Say that again. It's a very good question. Remember, so the question was, what does the shape of the Fermi level here look like? Okay. Now recall that the Fermi level. So remember the concentration of carriers. Is proportional to minus. Okay, so the concentration of carriers is exponentially related to the difference of the Fermi level from the conduction band for electrons or valence band for holes. Which means that if this is an exponential change, which we know it is, in space, okay, because we solved the diffusion equation. Okay, I'm going to, I don't recall the actual numbers, but this we know in space is some constant times an exponential relation, right? Minus x over e or something like this, right? Now you see that you can relate these two, they're both exponents, you can see how, now this, of course, becomes a quasi-Fermi level, okay? Because they're both exponents, you can equate the two factors on the top, and you can see that of course, the conduction band is basically what it is, right? It doesn't change, except for the bending at the junction, so ignore that. The quasi-Fermi level goes linear with x. Okay? See this, right? We'll do this more rigorously, but you see the point, which is basically what you're saying. The quasi-Fermi levels basically have a linear, it's a fixed slope, it's a straight line, because this is an exponential dependence. And they're related. Those things are related. Okay? But you can have more complicated things, obviously. Okay, so under biased equilibrium, Fermi level splits into two. Recall that the Fermi level determines the carrier concentrations at equilibrium. When voltage is applied, the carrier concentrations change with position. This change is represented by the position-dependent quasi-Fermi level. So the Fermi level, instead of being constant, now has a position dependence. That's the key point here. Which, of course, one would expect this to happen in any situation where you have a concentration, carrier concentrations that depend on position. Right? Anytime diffusion happens, you would expect this to happen. Under non-equilibrium conditions. Under equilibrium, they cancel out. So diffusion and drift in the case of the PN junction, for instance. So the quasi-Fermi levels on the two sides are separated by the applied bias voltage. So it should be pretty straightforward for you to calculate, for instance, where the quasi-Fermi levels are with respect to the bands, right? Because you know the equilibrium Fermi levels you already know if you know the doping. Okay. You know the band bending, again by the doping under equilibrium. And if you know the applied voltage, you know how much the band bending has changed, and that's the difference between the two quasi-Fermi levels as well. So you should be able to draw something like that, given all the parameters. Okay. Under forward bias in the depletion region, so if you look in the depletion region, we can write the expression for the concentrations. Remember the product of the N and the P is given by an I squared times e raised to the difference in the Fermi levels. Okay. Now this comes from the definition of the Fermi levels, right? You take this thing and then you have another guy here. And you multiply these up. We did this for equilibrium, but the same thing applies for non-equilibrium as well. You get an expression like this. Now you can see the interesting thing here is that you can see that the concentration, the product of the concentration is now proportional to the applied bias voltage. Okay. Now, if the applied bias voltage is 0, you can clearly see that the concentration is just the N times P is just the Ni squared. Right? It's just the intrinsic concentration, which is what you expect under equilibrium. Right? N times P is always Ni squared under equilibrium. So it's consistent with what you have seen before. Now, let's look a bit more closely at the spatial variation, which is basically reiterating what I approximately talked about here. So the minority carrier quasi-Fermi level varies with position. Like I said, it's a straight line, as we just talked about. The majority carrier quasi-Fermi level doesn't vary much. Now, the reason for this, I want you to understand intuitively, is because on this side, the majority carriers there's a lot of them, right? There's 10 raised to 17 or 10 raised to 20 or whatever. So the excess carriers that have been injected doesn't really change that very much because that's orders of magnitude smaller. So the majority carrier Fermi level really doesn't change too much. Okay? Strictly speaking, it does change a little bit. Same thing happens on the other side. The electron Fermi level in the N-type material doesn't change much. The whole quasi-Fermi level in the N-type does change. Okay? Outside the depletion region, the minority carrier quasi-Fermi level varies linearly with position because of this, which we talked about. Okay? This represents the exponential decrease in the minority carrier concentration due to diffusion and recombination. So it comes from the solution of the diffusion equation. Okay? So everything should kind of fit together. So the other picture is that it takes several diffusion lengths for those carriers to essentially die off. The excess carriers to essentially diffuse and recombine. So one would expect after a few diffusion lengths, that these two Fermi levels basically meet up, because the excess carriers disappear, basically, right? They recombine. It reaches the intrinsic concentration, FP crosses the EI. Okay. Oh, sorry, the other thing to think about is you have an intrinsic band energy level, which is roughly the halfway in between the band gap, right? So you can also calculate at what position will the excess carrier concentration, or the total minority carrier concentration, reach the intrinsic level. Okay? Because you can, so this is a little bit of a subtle point. You can have a situation where this injection is so high, but still lower than the majority carrier concentration, that this concentration here could be higher. Remember this, the minority carrier concentration could be higher than the intrinsic carrier concentration. Okay? That's the regime of high current injection, and it's typically how it's operated. Do you see what that means? It means that you have a pretty big jump in the minority carrier concentration pretty rapidly. Okay? This has important implications for the switching speed and so on, as we will talk about later. But keep that in mind. Essentially what that means is that this can split quite a bit. And of course, that means that you need a high voltage. Or you need to play with the doping, as we will talk about. Okay? So again, this is a important enough idea that there are different ways to look at it. Again, like I said, the point I want you to take is not really the math, because you can look it up in the equation, but it's the physics. You need to have a feeling for what these things mean. And this is a different way to think about it. So far we talked about carrier injection and the diffuse and recombine, which is, I would say, an easier way to think about it, right? That's relatively straightforward. Another way to think about it is in terms of the stored charge. And let's look, and they agree with each other. It's the same physical reality, it's just a different ways to think about it, okay? So again, we have the same kind of distribution. But let's think about what's really going on. Let's focus on the end side for a second, okay? So over here, you have injected holes. Okay, from the other side, came here, and you maintain this kind of a distribution. So these holes are diffusing and recombining with electrons. Okay, this injected current, so the holes are moving this way because of the diffusion, so you have some current flowing, supplies carriers to maintain the excess distribution of charges, right? So if this current moves and recombines, some holes disappear, so they need to be supplied. So you have a constant supply of holes coming in. So far, so good. Another way to think about it is, there is this region here, which is the excess charges that have been injected across, represents essentially a capacitor, right? Because it's a storage of charge, but it's a time-dependent storage of charge. So you have a region where there's a bunch of holes, essentially, positive charges, okay? But it's changing over time. They're recombining with some lifetime tau p. Okay? So every tau p seconds, which is the lifetime of the average lifetime of the holes, you have to replenish this charge, which is the injected current. So you can think about it that way as well. It's a time-dependent capacitor which is getting replenished. Okay? The charges are getting replenished, so you can calculate the current that way as well, which is what's shown here. Well, first, we reiterate the approximation. Charge control approximation essentially means this is what I said before, so it's nothing new. Minority carriers injected into either side of a p-n junction, diffuse into the neutral material, and recombine with the majority carrier. Essentially, it's saying that there is no recombination within the depletion region. So any carriers that get injected across, they make it across to the other side. It's the same thing, okay? So that's straightforward. The minority carrier diffusion current decreases exponentially with distance from the junction. We know that. A few diffusion lengths away, most current is carried by the majority carriers. Now, let's look at the math a little bit. So again, keep this in mind. You have injected charges across, and those charges, that if you look at that whole bar of semiconductor, those charges are getting replenished over time, which means that the average total charge there divided by the average time it needs to be replenished should give you the current, right? Charge by time is current. The rate of replenishment of this charge is current, essentially. That's the different way to look at it. So the total injected positive charge, so you have to calculate the total charge in the excess hole concentration at some instant of time is essentially the integral under this curve. Okay, you integrate the excess charges. So this is snapshot in time. You take an integral, and this area under this curve gives you the total charge, which is shown here. Q is the electronic charge. A is the area, cross-sectional area. You take an integral in x, going from 0, that's at the edge of the depletion region, all the way to the end of the bar, infinity, of the excess carrier concentration, and you can work that out. It's pretty straightforward, just an exponential. You get a very simple expression. So that's the average charges stored under that curve, the excess charges that have been injected across, essentially, every tau p seconds, because this is the excess charges that exist at some instant of time in that distribution. So if you think about the neutral region of the pin junction and the capacitor, that's the amount of charge that's stored on one side. Okay? And this model of the capacitor becomes important when we talk about switching times. It's exactly the same as you do in circuits, which you've seen before. Okay, we'll come to that. So the average lifetime of a hole is tau p, which means that on an average, the entire charge distribution, this is the total charge, will recombine in tau p seconds and must be replenished. Remember, this is a steady state, so these charges disappear. More charges have to come to take their place, right? Otherwise, you'll have some transients. Then the injector hole current is very straightforward. You take the total charge divided by the average time, and you get the current. And it's exactly the same expression that you had before. Okay? You will see. We just have to substitute the expression for delta Pn, which, remember, is exponentially dependent on the voltage, right? E raised to qv over kt minus 1 and all that. Okay? Okay, so Lp over tau p is dp over Lp. The diffusion coefficient is related to the diffusion length and the minority carrier lifetime. We defined all this later, so it's a simple substitution there. So let me just go back. The picture which is completed here is that the current here plus the current here will give you the previous diode equation as well. Okay? That's the principle. Okay, so that basically brings us to the end of that chapter. But again, this is important enough that I wanted to re-emphasize the two ways to look at it and how to calculate current, because this is basically how we will describe devices as we go along. So you have to really understand this, and we will apply basically the same thing for different kinds of devices. Basically, that's it. So make sure you're pretty clear on this end. So let's look at this. To summarize again, the current at the PN junction can be calculated using two methods. One is the charge, and one is carrier injection. The carrier injection is pretty straightforward. You have, majority carriers get injected, they become minority carriers, they diffuse and recombine. You solve a diffusion equation, you get an exponential decay. Okay, that's the picture I want you to keep in mind. Okay, and that exponential decay is the steady state distribution. And what you want really is how do you relate this to the bias potential. Okay? The bias potential, of course, increases this injection because you're reducing the energy barrier. So remember, here there was an energy barrier which we talked about last time. When you forward bias it, you reduce the energy barrier, you have more carriers that get injected. Okay, so that's how current increases. If you reverse bias it, you increase the energy barrier, fewer carriers get injected, current decreases. Okay, that's the picture you need to keep in mind. The equation's not that difficult. Okay, and the current looks like that and so on. Another way to think about it also is that the slope at the transition region from the depletion region to the neutral region defines the current. Right? Remember, the gradient of the concentration defines the diffusion current. So the slope here, which is the gradient, defines the diffusion current, which is exactly the same as you did before. So you don't need to be alarmed, but you can work out the math. It's not terribly complicated. It's exactly the same thing. The second approach is basically what we just said. It's replenishment of the charge. Because you have a certain number of charges, they get replenished every lifetime. Again, the fundamental assumption is that there's no recombination in the depletion region. Current at one location is calculated. Okay, we can calculate the current here, the whole current here, the electron current here, the whole current here, add them up, that's all you need. It's exactly the same current everywhere else. And the reason is because we assumed there is no potential drop in the neutral region. Right? We assumed it was a perfect conductor. It's not strictly true, but it's an approximation. Okay. So we saw that. We saw that. I'm not going to go through the math again. Okay. So let's look at a different question. Okay. So the question then we can ask is, how do we calculate the majority carrier currents in the neutral regions? We said early on when we talked about this that the current in the neutral regions are carried mostly by the majority carriers, first of all, right? Which makes sense. Why? Because far away from the junction, okay, there is no gradient, right? Because all the excess carriers have basically died off. Okay, so you expect very little diffusion current, right? That's obvious. Because remember, if you go back here, far away from the junction, this basically is zero, right? There's no diffusion current. That's a minority carrier current. So but there is current, right? There's current happening. I mean, there's current flowing here. How is that flowing? The only likely explanation is the majority carrier. The drift current from majority carriers. Okay? Something has to flow here, otherwise. So the question that's being asked here is, what is the physics behind that flow? What's carrying the current here? Essentially the majority carrier. And we can look at this in this interesting plot. Okay? So this is plotting current as a function of position across this PN junction. So remember what I said, the total current across the PN junction is exactly the same. So if I plot the total current, it should be a straight line. Okay? Indeed it is. It is that straight line. Total current across this PN junction is exactly the same. Okay? Now let's look at what creates this total current. In the junction, or near the junction, we already know, it's mostly the diffusion current. Right? We just calculated. Okay? So let's go through it. The total current is the same throughout the device, given by the diode equation. Okay? So it doesn't vary across position. So this X represents this position across this P plus N junction in this particular case. Okay? So the minority carrier diffusion current decreases exponentially due to recombination of injected carrier, minority carrier. So again, near the junction, so let's point out the two curves here, first of all. The dashed line is the whole current. Okay? The solid line is the electron current. Okay? So far, straightforward. Near the junction, within the junction, of course, the currents really don't change very much because it's basically a drift, right? You get swept across. So let's ignore what's right in the depletion region because it's just the electric field. Nothing too interesting. But right outside it, it is the diffusion current. So here, the minority carrier, so this is the minority carrier current, right? Electrons in the p-type material. It is diffusing and recombining. You have an expression which looks like that. Spatially varying. Okay? Why does it look like this? Because it is basically proportional to the gradient of the concentration. Okay? Now, without going into detail, you can very easily know that the concentration gradient is an exponential. The derivative of an exponential is also an exponential. So the current has to be an exponential as well. Decreasing exponential, right? Remember that the diffusion current, which is the minority carrier current, because remember the majority carrier diffusion current is very small because there's very small change in the diffusion, the concentration gradient of the majority carrier. The diffusion is proportional to the rate of change of the minority carrier. So in the case of the N, the electrons in the p-type, right? Is that. Now we know that this is exponential because that's what we solved, right? We solved the diffusion equation, you get an exponential decrease. So obviously if you take the derivative of an exponential, you get an exponential. So the current also must be an exponential decrease. Okay, pretty simple. So on the other side, the same thing for the minority carriers on the N-type, which is a whole current, should also be an exponential decrease. Okay, so far so good. And we said that we just add the current here and the current here and you get the total current. Right? We looked at two different positions and we add them up. But if you look at a single position, the total current is made up by the diffusion current of the minority carriers plus some drift current of the majority carriers. Okay? This excess current here is what gives you the total current here. So you have electrons here diffusing, and you have holes here also diffusing, but now it's diffusing in the opposite direction. Sorry, it's not drift, it's diffusion. We'll come to drift in a second. Now, what is the physics of that? Why is there a hole diffusion here? Okay. There is hole diffusion here because there is recombination happening. These excess electrons here are diffusing with holes. I mean, they're recombining with holes, right? So you're losing some holes near the junction. Far away from the junction is lots and lots of holes. Near the junction, you're lost a little bit of holes. So you have a concentration gradient. So holes will come in to fill that up. So you get a diffusion current of the majority carriers. Okay? That's the picture that you want to keep in mind in this. Well, the heat comes from resistance, which is the lattice, collisions with the lattice. The electrons and holes collide with the lattice, create heat. They lose energy. That's the primary reason. But we'll talk about some other things too, related to what you just mentioned. Okay, so the majority carrier component, far away from the junction, of course, there's no diffusion because the concentration gradient is very small. So the only thing that can be there is drift. Okay? So the majority carrier component must increase exponentially to maintain the total current constant. The physical picture is what I just said, but again, to reiterate, is that electrons must flow. So on the n-type, the electrons must flow from the n-type to replenish the electrons lost by recombination with excess holes near the junction. These electrons come from the battery. Okay, so on the it's exactly the same thing that I mentioned for the p-type, but on the n-type, you can see because the holes are here recombining with electrons, you get there must be electrons coming in to compensate for that. And of course, those electrons have to come from somewhere. Outside the semiconductor comes from the battery. That's the current. Okay. Now, looking at this in a bit more detail, let's see the time. Okay. Near the junction, you have a mix of drift and diffusion, like I said. Far away from the junction, you have mostly drift. Okay, so near the junction, you have a drift, partly drift and partly diffusion. But for majority carriers, drift dominates. For minority carriers, you have this diffusion. This means that out here, first of all, the carrier concentrations are constant, right? So you can only have drift, which is what I've mentioned. But that raises an interesting problem. We assume that there is no field out here, remember? How can you have a drift current without field? Okay. So obviously our assumption that there is no field there is not quite right. Okay. That's another important point to keep in mind, that in order to have current out here, there cannot be diffusion current because there's no concentration gradient. It can only be drift. And for drift, you need to have a field. Okay? In order to have a field, you need to have a potential drop here. But our assumption is approximately correct because you only need a very small field, as long as this is heavily doped. Okay? Because with a small field and lots of carriers, you get sufficient drift current to make up for the difference. That's the idea. So, this means that our previous approximation that there is no field in the neutral regions is not strictly correct. Otherwise, there will be no drift current. Nevertheless, since the carrier concentration is large, only a small field is required. Okay, so the picture. Again, let me just reiterate this picture. So we have majority carrier injection here. So minority carriers on this side, they will recombine and diffuse. Okay, that recombination must be compensated by some drift current for the majority carriers coming in. Okay, and the sum of these currents gives you the total current. And of course, the majority carriers coming in the case of holes, is coming from the battery from this way, from the battery from this way for electrons. Okay? That's the picture I want you to keep in mind. And the expressions are straightforward. Okay, so we have an example problem from the text. So let's try to do this using about a minute or so. Find an expression for the electron current in the n-type material of a forward bias p-n junction. In other words, find the electron current, so this plot right here, for forward bias p-n junction. Okay? And we'll work through it together. So think about that for 10 seconds while I find the example. Okay? So, so first of all, the thing we know is that we know the diode equation, right? So an applied voltage, we know that the current is given by I naught times e raised to q p over kp minus 1. Right? This we know. Applied voltage at this time. This is the total current. So this is made up of some hole current and some electron current. The question is to find this. Okay? There are a number of ways you can solve this. Okay? One simple way is this on the n-type side. The whole current here is because of the diffusion, right? And that's easy to calculate. Is given by the diffusion equation. So it's Q charge A diffusion coefficient times the exponent, right? So the exponential increase. Okay, that's straightforward. Okay, this is the exponential decay because of the combination and diffusion. And that's the voltage component because it determines the energy barrier. Now you know these two, you need to calculate that, that's pretty easy. Subtract that. Okay? And if you do this, you can see two terms essentially, okay? You have a term which comes from this I naught. Okay, so if you do this, you will see that there's these things are the same. Right? So you have this thing minus I naught minus this thing, right? This part right here. And then you plug in the value of x. Okay. So you can see there are two terms. One is because of diffusion, and one is because of the drift. Which basically says the electrons supplied for recombination with the injector holes and the injection of electrons across to the inside. Okay, there are two things happening, right? So keep that picture in mind. So what do electrons do over here? The electrons have to recombine with the holes, right? So those electrons have to be supplied from the battery, like I said. But also, electrons get injected across, right? So there's carrier injection to the other side as well. You have two terms, so that's the carrier recombination and the carrier injection. And when you subtract this, you'll get those two terms. So this is the expression for that. Okay. So again, you should be fairly comfortable with following the logic. I don't really care about the math so much. Okay, so that was the end of that topic, and then let's start with the next one, which is on the, let's see. We'll look at the time dependence of the current. Okay. Oops, wrong one. Okay. Oh, yeah, two more things actually. Before we go to time dependence, we want to talk about the reverse bias. So far we've mostly concentrated on the forward bias. And under forward bias, we have a fairly complicated situation of carrier injection. We do a combination of this. Under reverse bias, the situation is a lot more simple. Okay? But we need to understand it physically as well. So what happens under reverse bias? Okay, the picture, if you look again from the picture that we had before, is the opposite of carrier injection. Okay? It is carrier extraction. You pull the carriers out to the other side. And you can, let's see what that means. So you have a P plus N junction here. Okay? If you look, when you apply reverse bias, of course the depletion region gets bigger and you increase the field. Okay? When you increase the field, what happens is that any carriers that accidentally get here, they get swept across. Right? You increase that drift field, the built-in field, essentially. Okay? And you essentially lose carriers from one side. So you lose the minority carriers. So in the case of the holes, a p-type, you get electrons here that get pulled across to the other side. So you lost the minority carrier. So you have a carrier extraction, which goes the opposite way. Okay? Now, of course, if you plot the carrier concentration as a function of position, you have the opposite. You have a decrease in the carrier concentration, and then it increases far away to the equilibrium value. Okay? Now, the excess carrier concentration here can be shown to be, if you have a sufficient reverse bias voltage, exactly minus of the equilibrium concentration. So the total carrier concentration right at the junction can be shown to be 0 when you have sufficient reverse bias applied. Okay? And it's easily proven from the equation here, it's exactly the same thing we derived before. Delta Pm is Pn e raised to QV of Kt minus 1. But now V is minus Vr. Okay? It's a reverse bias voltage, so it's negative. You apply enough of this value, this goes to 0, and then delta Pn becomes minus Pn. Pn, remember, is the equilibrium hole concentration on the n side. So the excess carrier concentrations become negative, which means the carriers have been lost, they have been extracted away, and the exact number is equal to the equilibrium concentration, which means that the total carrier concentration there is basically 0, right at that boundary. Okay? This means that the minority carrier concentration is 0 right there. Of course, which also means the quasi-Fermi levels have to split and all the same thing that happens within the opposite direction. Okay? Same thing for the electrons in the p-type. Now, to look at this closely, we can calculate the excess carrier concentration with the same expression as before. Now, because it's decreasing towards the junction, you would expect diffusion to come towards the junction as opposed to be away from the junction, right? So if you look at the electrons in the p-type material, they will diffuse towards the junction because the carrier concentration looks like that. And you can solve the diffusion equation again, and expression basically becomes an exponential. Okay? This is basically explaining that. And you can calculate it in exactly the same manner as we did for the forward bias. You get the same kind of plot, but it's the opposite direction, that's all. Okay? So delta NP times e raised to minus xp over ln, ln being the diffusion length of the electrons, then you get an expression that depends on the voltage here. So, okay? And the same thing happens for the holes, exact same expression. So you have a diffusion of holes which come from far away from the junction towards the junction, which is the opposite of what we saw before. And remember, this diffusion is now in the n-type material. It's a minority carrier diffusion that's happening. So the current is now in the opposite direction, right? You see that. Earlier, remember, the holes were excess carriers here, right? They were going down like this. Now it's the opposite direction. The diffusion is in the opposite direction as well. Current is in the opposite direction as well because it's reverse bias. Okay, so everything again is consistent with the picture you had. And that's, V is negative, so you have minority carrier extraction. This V is negative enough, then this number becomes minus Pn. Okay, so you just saw. Essentially, the picture is that the holes are swept across by the field. Like I said, when you do reverse bias, that field is increased, it gets stronger. So any hole that accidentally gets into the depletion region essentially gets swept across really fast. Okay? And if your field is large enough, you can actually tear the electrons and holes out of the covalent bonds. We'll talk about this. And they can sweep across the junction as well. Okay? And that's a very specific phenomenon for reverse bias. Because you extracted the holes from the n-type to the p-type, you create a concentration gradient which causes this diffusion. The holes diffuse from the neutral regions towards the junction, like we said, and these holes are generated. So this diffusion, of course, means that the holes have to come from somewhere. Okay? And they have minority carriers, remember. Okay? So there are not a lot of them around. They have to be thermally generated minority carriers. Okay? These holes are generated thermally within one diffusion length of the junction. In other words, you need to have enough holes near the junction to compensate for this diffusion, to contribute to this diffusion, not compensate. Okay? If they are far from the junction, they will not diffuse long enough to really contribute. So the generation that happens right near the junction contributes to the current. So that's why it's also called the generation current. This is the I naught. This is this thing right here under reverse bias, right? Minus I naught. That's also called generation current because it's determined by the thermal generation. Now, if you look at the band diagram, it's the opposite of what we saw before. So first of all, we are familiar with this now, that the energy bands are bent more. Okay, you've increased the energy barrier under reverse bias. That's conduction band, valence band. If you look at the quasi-Fermi levels, the behavior is the opposite of what we saw before, and it can be explained by what we see in the carrier extraction. So far away, of course, it's still the equilibrium. Nothing's changed. As you get closer to the junction, they split. So because now this is the p-type, we have lost electrons. Remember, the electrons have been extracted. The minority carriers have been extracted across. You would expect the Fermi level of the quasi-Fermi level of the electrons to move further away from the conduction band, right? Because you have fewer electrons. The difference between the Fermi level and the conduction band determines how many electrons there are. Fewer electrons means this has to increase. Okay? So the quasi-Fermi level for electrons goes down. Quasi-Fermi level for holes stays the same, roughly. On the other side, the opposite happens. Far away, it's still the equilibrium. But now, it's the n-type, the holes have been extracted across. So the quasi-Fermi level for the holes have to go away from the valence band. So it goes up. Okay? So you see a splitting up and then meet in the middle. And this difference between the quasi-Fermi levels right here is the applied voltage, reverse bias voltage. Okay? And of course, it makes sense because you have a carrier extraction, right? You have fewer electrons right here, fewer holes right here, and everything makes sense. And there's diffusion that compensates for those. The fewer carriers are in equilibrium. In the depletion region, interestingly, if you look at this situation right here, Pn equals Ni squared, the same equation that we had before. Fn minus Fp is now very large negative number. I mean, not very large, but it's an exponential. So any even small negative number will make this whole thing basically go to zero. It's saying that under reverse bias, there are very few carriers in the depletion region, which we know because there's a high field, right? Any carriers that get in there basically get swept across. So it makes sense. Okay. Okay, so let's look at this example problem. And I want you to think about this actually. Try to do this yourself. It'll take about a minute or so. So let's see. I haven't actually made your midterm, but you can expect things like this, I would say. So try to do it. An abrupt silicon p-n junction, so it's a sharp junction, p-n-n. Area is 10⁻⁴ centimeters square, has the following properties at 300 Kelvin. Okay? If you have p-side acceptor concentration, the electron lifetime, mobility of the holes, mobility of the electrons. On the n side, same thing, donor concentration, mobility, lifetime of the holes, mobility of the electrons, mobility of the holes. The junction is forward biased by 0.5 volts. What is the forward current? It's very standard, right? This is the sort of stuff you should be able to do. What is the current at reverse bias of minus 0.5 volts? Okay, I want you to, you can discuss with your neighbors if you want, or just do it yourself. Spend about 30 seconds to a minute thinking about this first, how you would approach the problem. Okay, where would we start approaching this problem? Yeah, the goal is to find current given a voltage. You start with the diode equation, the simplest thing, right? Okay, everybody should be clear on that. So you start with the diode equation. Okay, you're asked to find this given that. Okay. So far, it's pretty straightforward. Of course, all these things are constants. The only thing you need to really know is that the reverse saturation current. Okay, so let's think about what that is. So any thoughts? Okay. We calculated this the last class and today. Reverse saturation current is given by some diffusion terms, right? Remember, it's a diffusion of electrons on one side. It's a carrier injection. There's diffusion electrons on one side, diffusion of holes on the other side. Okay? The diffusion current is basically, which is volts, is something like that, times the concentration of the holes right at the junction, plus the diffusion of the electrons, times the concentration of the electrons right at the boundary between the depletion and the emission region. And of course, this is multiplied by Q, the electronic charge in the area. Okay. Okay. That's okay, right? This is just the diffusion current. Remember, this is the slope of the curve right at the boundary. Okay. So we know this, the constant. We know the area is given. In this part, we need to calculate. So let's look at this. So first of all, what's given? Do we have? Okay, not too much, I guess. We need to calculate. So let's start with Pn. Okay. Pn is the minority carrier concentration on the n-type. Full concentration on the n-type material. You should be familiar with this, but you can use the expression that this is Ni squared times n times P is Ni squared. Okay, this is the equilibrium concentration, right? Even though the whole system is not under equilibrium, these things are for equilibrium concentrations. Okay. Why? Because we have already taken that e raised to minus x over LP into account already, so it's already there. Okay. So this stuff you can calculate. The Ni squared you know because the temperature is given. Okay, or your terms of temperature. And N is what? This is the majority carrier concentration in the n-type material. What is it? Someone said it actually.
Would it be ND?
Yeah. Right. Because it is heavily doped. You can just make the assumption, right? That's okay, right? That should be pretty obvious. Okay. So you know this now. You know this part. This thing, NP is the same way. You have a Ni squared divided by Pp, which is the majority carrier concentration of the holes in the p-type, so the concentration of holes, which is the acceptor concentration pretty much. Okay, so also need this. Now you need these things. These things have material constants, and you just look it up. I mean, you can look up the ways to calculate it, but so here they do it with the Einstein relations, remember, because mobility is given. You can calculate the diffusion coefficients. The ratio of diffusion coefficient to mobility is given by kT over Q. Right? So also, it's the Einstein relation. So you know this, mu p and mu n, these things are constants. So you know this, mu p and mu n. Calculate that. Okay? So you know that. So all you need now is the diffusion lengths. But you know how to relate diffusion length to diffusion to the lifetime. Okay, we talked about that also. So the diffusion length related to the lifetime by that. Okay. And that's all you need. Now you know everything. From these and from knowing the lifetime, you know all the terms. You plug it in and get the current. Okay. So just make sure you follow the logic again. Don't really. You look up the equations. You don't need to memorize any of this. So for reverse, so half volt forward bias, you get the answer here is about 1 microamps, and in reverse bias, again you do the same thing. You plug it in, minus 5 volts, and you see the answer is about 10 raised to minus 15 amps. So it's very, very, very small. Okay, this is what you expect for a good diode. By the way, this is, you can see, it's not really a P plus N junction. It's only 2 orders of magnitude different, right? It's not a great diode from that perspective. Okay? And you can see the big difference in the mobilities and so on, right? The mu P here is twice as much as that. The mu N here is twice as much as that, which suggests that there are 2 different materials and so on. So these kinds of things are what you actually make in your diode, right? So you know these things because you design these things. Remember, the mobilities you can measure from the Shockley, the Hall experiment, right? Okay, all of this you can measure, lifetime from the Haynes-Shockley experiment and so on. Okay? So this is a very realistic scenario in terms of calculating current voltage relationships. Okay. Okay. Yes. Yes, Ni is the intrinsic carrier concentration of the material. So let's see what it says silicon. So you can just look it up in the table. It's usually, for silicon, it's about 10 raised to 10 per centimeter square at room temperature. Yes, remember the intrinsic carrier concentration is the concentration of the carriers when there is no doping. So if you just take a natural silicon, piece of silicon, with no impurities in it, the number of holes should be equal to the number of electrons because it's a neutral material and there are no impurities. It's a perfect silicon material. That concentration is a property of the material and also a property of temperature. As temperature changes, it changes a little bit. And we talked about this in chapter 3, I believe. And there's a plot which plots the intrinsic concentration of function temperature. So if temperature changes, you can go back and look at it. But in the exams, I'll give you. So don't worry too much. But you should know what it is, what it means. It's a fundamental property of the material. Okay, so the under reverse bias, yes?
I actually have a question. The N sub D, that's in
This?
centimeters.
Yeah, this is out per, so the units are just showed on one side, yeah.
Just making sure.
Yeah. I'll give you all the units, but you should be relatively familiar with these things. Okay, so let's get started on this part before the end. Under reverse bias, there are a few interesting things that happen which are useful for real devices. Okay, there's something called reverse bias breakdown. And all this means is what's shown in this IV curve. Okay, you have current, you have voltage. The forward bias is exactly what you saw. Voltage increases, current increases exponentially. Okay, pretty straightforward. Under reverse bias, so far our model has been that the current is constant with voltage, right? Remember, here if V is very negative, this whole thing becomes just minus I naught, a constant, right? It doesn't depend on voltage, it's a straight line. Except when the voltage gets high enough that you get what's called reverse breakdown, you get a situation where the current actually gets really large in the opposite, in the negative direction. And that's called breakdown. This doesn't mean that the diode is damaged. Although breakdown suggests that that's a bad thing, it doesn't mean that's a bad thing. It can be bad. Of course, you can damage it as well. Okay. And there are, yes.
I just have a question on this.
Yes.
Yeah. So before you said if N or NP is small, you can just ignore it in the equation.
That's correct. Yes. Good point.
So then would we only have to, depending on the numbers?
Yes, only one side. That's exactly right. Yes, that's a good point, and that's what I said before, that this is not heavily doped on either side, so you cannot ignore one side. So imagine that this ND was, let's say, 10 raised to 11. Okay, that's 6 orders of magnitude larger. What that means, essentially, I mean, you can do the same way, still give you this correct answer, but you will see that one of these numbers will be 10 orders of magnitude bigger than the other. So when you add these things up, it will basically be just one term. But this is fine. You don't need to make any approximation. You can do it this way. Or you can make the approximation. That's fine too. Okay, as long as you're clear on what you're doing, it's fine. Okay, so the reverse breakdown essentially means that you get this huge current which flows through. Okay? Now, like I said, it's not necessarily a bad thing. It is actually useful for many, many devices. It's actually used in actual devices. So, but you need to be careful in the fact that if you have too much current flowing through a junction, you can create, of course, the electrons flowing through a junction means that they will undergo collisions. They will create heat. At some point, you get too much heat that you can cause thermal degradation of the material. So you want to maintain the current to some maximum value in the negative direction. The way you do this is by basically placing a resistor, right? So can someone tell me what the maximum current here is? Just looking at this IV curve. This you should have done in your freshman class, right? Yeah. What's minus I here? Ohm's law, right? It's just E minus whatever is the drop there divided by the current. I mean resistor, right? So think about it this way: you have a battery. Which way is it? A battery, a resistor, and you have something here which is the PN junction, it's a diode essentially. Okay? This has a drop of V breakdown. Okay? The maximum current here is basically E minus VBR over R. Right? So by choosing R high enough, you can make the I small, so you don't damage the diode. Okay, now let's understand what these things, what the mechanism is. If sufficient reverse bias voltage is applied, the current can increase dramatically with little further increase in voltage. This is called the reverse breakdown. Okay, so you get this big increase in current. And the voltage basically becomes fixed. That turns out to be an important point, as you will see. Okay? An external resistor may be used to limit this current to prevent thermal destruction of the device. There's a current here, we just did that. Some diodes do operate in reverse breakdown, and let's look at some details. There are two kinds of breakdown that happens under reverse bias. Okay? One is what happens under low voltages. It's called Zener Breakdown, or something that happens at high voltages, which is Avalanche Breakdown. Okay? Avalanche is very similar to what happens when you go skiing. Same thing, basically, but for electrons and holes. Okay. For Zener breakdown, the idea is also very straightforward. The idea is it occurs at low reverse bias voltages. It's under a few volts. Okay? And it's easily understood by looking at the bands. Okay? So let's look at the band diagram. So you have a conduction band, valence band. This is under equilibrium because the Fermi level is flat. Right? You can look at a band and that's another thing you need to be able to do. Look at a band diagram and tell me what's going on. Right? You should be able to answer that. Right? This is equilibrium. Now, when you apply reverse bias voltage, by the way, you can see that this is reverse bias, right? Again, that should be something you should be reasonably familiar with because you can see it's increasing the band curvature, right? The quasi-Fermi level split by a value equal to the applied reverse bias voltage. The depletion region width increases, all the usual stuff. Now, but you see something interesting happen here. If the bands have bent sufficiently enough, you see that the conduction band on the N side comes very close to the valence band on the P side. Okay? In energy. So this is energy. This vertical axis is energy, right? So they get close in energy. What does that mean? Let's look at what that means. So you have lots and lots of electrons here in the valence band, okay, which have about the same energy as lots and lots of free states in the conduction band. Now, if these bands are very close together in space, in other words, if this D here, which is of course determined by the depletion region width, is very small, then the electrons can tunnel across. It's exactly the same thing that we talked about in chapter 2, I think. So you have a small energy barrier here, and some of the electrons can tunnel across. Because the energy here is about the same as the energy there, right? It's the same vertical distance. And if the spatial dimension is very small, they'll just tunnel across. And this, of course, if the electrons tunnel from the p-type to the n-type, it's the reverse bias current, right? The current is in the opposite direction, n to p. And that's what's called the Zener breakdown. And the fact that the current can get very large is because there are lots and lots of electrons here, they're filled bands. Lots and lots of free states here because of the conduction band. So lots and lots of exchange can happen. Okay? Let's see, what else? So what is the direction of this tunneling current? You can see the electron goes from p to n. The current is from n to p, the reverse direction. Okay? This is called a Zener effect. And the requirements for the Zener breakdown are that you need to have very sharp junction, which means that you have very small transition from n-type to p-type. And you need to have heavy doping on both sides, so the transition region is very small. So this D here can be very small, so the tunneling can happen with high probability. Okay? W is small, and under reverse bias, the fields are very high. So if W is also very small, the electric fields get really high, which means that this bending becomes very large as well. You also need lots of bending for this overlap to happen. Okay, you see this. Okay. The physical reason for this is actually interesting, is because when the fields get really high, the electrons get pulled out of the covalent bonds of the silicon atom. Okay, and they break the bonds essentially, and they pull them across to the other side. That's another way to think about this tunneling behavior. Okay? The electrons in the covalent bonds of the atoms in the transition region are torn from their bonds by the high electric field, and it has to be like 10⁶ volts per centimeter or so, which is pretty high, and swept across the n-type region. And the picture there is exactly the same as here because of the very, very high fields, which of course is pointing from n to p, right? Donor atoms to acceptor atoms to donor atoms. And the electron gets pulled across because of this large field. Okay? Okay, I think we'll stop here. We'll talk about the rest of the stuff when I get back. So remember a few things, that there is no class on Tuesday. Okay? There will be a review session on Monday, which is a little bit longer than usual, and it will be a review for the midterm. So the midterm is the Thursday before spring break, and I don't remember the date. Okay? And I think there is a review session tomorrow with the usual problems. So again, none of this is mandatory. You can attend if you want. And I posted the topics that are important, I think, for the midterm online, so you can go take a look. But like I said, the most important things are make sure you're comfortable doing the problem sets and the examples in the class, and then you'll be okay. We have the whole class on Thursday before spring break for the quiz. And we have a lecture on Thursday, so don't come on Tuesday, but make sure you come on Thursday. Because that's the optical absorption, which will be on the next problem set, but not in the quiz. So, yes?
So the review for the midterm is what time?
5 to about 7.
5 to about 7.
Yeah, I mean, depending upon, again, try to bring your questions. If you have questions, you want clarification, take the opportunity to do that, okay? Oh yeah, there are problem sets here that you can come pick up.